Hello everyone, let's solve this problem. This problem I'm trying to do is LeetCode. LeetCode this one, number 286, because I don't have the membership of LeetCode. So now I'm using the LeetCode for solve this problem. So I'm using here. Okay, so let's see the description for this problem. So you are given a m times n 2D grid initiator with those three possible values. Okay, so we can see from here. Okay, three different values. So the first one is -1. -1 is a wall. Or something we cannot get it. It's blocked. Okay, so and then 0, 0 means a gate. Okay, and then infinity. Infinity means an empty room. Okay, so we're using the NFS to represent the empty room. Okay, so what we're gonna do? We are fill every single empty room with the distance to its nearest gate. Okay, so let's say for example this one, this empty room, the nearest gate is going to be here, right? So it's going to be 1. So the result here is 1. And then this one, the nearest gate will be here. We have 2 gates. Okay, so we go here is step 1. We go here 1, 2, 3, 4. Will be 4. So we update this one is 1, and this one is 2. The distance from this empty room to the gate is going to be 3, and this one is 4, right? So this is basically the description of the problem. So when we solve this problem, so we assume our maximum of empty room is m by n, right? Here is already given. Yeah, already given m by n. So we have k gates. Okay, so when we make this problem, what we do? We will ask the interviewer, what if k equals to 0? That's a corner case. What if k equals 0? That means we have a 0 gate, right? What if we don't have a gate? So how to update the infinity, or how to deal with the empty room in this situation? So we're just trying to communicate with the interviewer. Okay, so we are trying to interact with our interviewer. Okay, now so for this problem, we have different ways. Okay, so the method 1. So for every single empty room, every single empty room, we will fill with the distance to its closest, is the nearest gate by using DFS. Let's try to explain this way. So for this empty room, so there's 2 gates, right? So the closest distance to each gate, let's say, so this distance 1, 2, 3, 4, and from here to 1, 2, 3. That means that from this empty room, we are updated. We'll fill here with 3. 3 is the distance to its closest gate. Okay, and then we can update this one too. We can see the gate is here. So 1 step, 2 step. So we can arrive this gate. So that's why here is 2. But if we go here, let's see, 1 step, 2 step, 3 step. So if we trying to reach this gate, gonna be 3 step. But if we reach this step, this gate is gonna be 2 step. Okay, so this is basically the algorithm for the method 1. So, but we will do k times of BFS. Okay, because for every single empty room, we are doing BFS, and then we update the distance. So for the time complexity for this problem, is gonna be mn times mn. So mn is the let's assume the maximum of empty room is gonna be mn, right? So we have and then we do we do how many times? We do mn times BFS. So each BFS, the time complexity for each BFS is big O mn, and we are doing mn times. That's why our time complexity will be like this. Okay, this is a time complexity for this method. Also, we can have another method. So we have another method for every single gate. This is a gate. For every single gate, let's say from here. For every single gate, we will fill with the distance to each empty room. We will fill this to each empty room. And we will find and update the shortest distance to each empty room by using BFS. So how do we do? Let's say from here, the distance to this empty room is 1. The distance to this empty room is 1 also. Here is an example. So what we do, we just update here is 1. Okay, and here is 1. Okay, and then we will do the BFS for this one because it's in the corner, so we don't have to do more. We return. And this one, we will update this distance. This distance to this gate is gonna be 2, right? We are doing BFS, so it's gonna be 2. Okay, and then here is gonna be 2 as well. Right, we are updating and then for every single 2, what we do, we will update like this one gonna be 3. The distance to here, right, is gonna be 3. And then we update this one. This 2, the neighbor of for this direction is gonna be 3. Right, the distance to here is gonna be 3, and then from this 3. Let's do here. So from this 3, we updated the both neighbor of here. This one is gonna be 4. Okay, this one is gonna be 4, and here is gonna be 4 too. Okay, that means is a 4 step to this gate. So 1 step, 2 step, 3 step, 4 step, right? Here is the same, and then we update this 3 for we have one more step here, so it's gonna be 4. Okay, if we reach this one. So and then this start from this gate. Let's say this gate 1, right? And we have another gate 2. So if we start from this gate, how do we update? Okay, if we start this gate, so yeah. So how do we update? So we will go this way. So here, the step to here is gonna be 1, right? It's gonna be 1 here, right? And then to here is gonna be 2. And then this one is gonna be 3. It's gonna be 3. And then we will update this one. This one is gonna be the 1, 2 is gonna be 3, right? And here is gonna be 4. It's going to be 4. This one 3. This one 2. And then we will update. From here we reach here. We will do this one is a 5. Okay, and this one is a 6. Okay, this one is 7. Okay, so this is basically the path we are doing. Okay, so but we are but our goal is to find and update the shortest distance to each empty room. So we have to compare. Let's say this one 1 and 4. So which one smaller? Right? 1 is smaller. 2 and 3. Which one smaller? 2 is smaller, and this one is smaller. Right? So So, and then the 3 and the 2, which one is smaller? 2 is smaller, right? So we have to update. We have to update this way, right? So, and then we got this answer. This is method 2. For this one, we compared this the first solution, the second solution. Which one is better? Apparently, this one is better if k is smaller, far smaller than the empty rooms. Okay, so let's say we have m by n, and then we only have one gate. So in this case, we will use the second one. So we start from the gate and update every kind of the distance to each empty room. This this time complexity will be smaller. So let's talk about the time complexity. So we have k gates, right? So we using BFS to update the distance, right? So the time complexity for the BFS is gonna be OMN, and we have k number of k gates, right? So that's why when k is very smaller than the MN, than the maximum of the empty room. So in this case, we will use the solution 2. But can we do it better? Can we do it better for the time complexity? Yes. So we can actually use this method. We can call it a multi-BFS. So what does that mean, multi-BFS? Multiply BFS means that start from every single gate. Here's a gate, right? And then we use the BFS to update the distance to its nearest gate. Okay, so we do this at the same time. So we will put all the gates to our queue. Okay, we put this one and this one to our queue. And then what we do, let's say here we have a queue. Okay, so what we do, we update this one to here is 1, right? It's gonna be 1. And this empty room to that gate is gonna be 1 as well. And this one is gonna be 1, right? Yeah, because we put the both 0 to our queue. Okay, so we update this one, and then we update this one as well. And then we put this 3 to our queue. And then we will pull this out. We will check if any empty room in this neighbor. No. And what about this one? Yes, we do have this direction and this direction. So this direction gonna be 2, right? So this direction here is 2. And here is also gonna be 2. Here is also gonna be 2. And what about here? Here is also gonna be 2. Right? And then we just updated this one, so we don't have to update it again. So and then start from this 2, let's say. So 2, we will check this this empty room. So the distance to the gate is gonna be 3. So after we update this one is a 3, so we don't have to actually check this way because we are checking we are using the BFS, right? So we are just one step. So one step we around here, and then let's check this one. This is blocked. This one already visited. This already visited. So we just return. And what was this one? The down direction is already visited. This one visited. This one is out of boundary, and then we update this one. This one gonna be 3. Right? And then we have 2, 3 now in our queue. So we will pull this out. And then we will update this one is 4. And then we put 4 to our queue. We offer 4 to our queue. And this part we don't have any neighbor is never visited, right? So and then this one we don't. So the neighbors already visited or out of boundary. So and then this is our answer. See, it's exactly same as this one. So for the multi BFS, so what's the time complexity? Actually, it's the same as the one we just used. So the time complexity will be mn. The space complexity is also big O mn because the worst case, so we will put all the cells to our queue, right? So the space complexity will be OMN. So this basically the algorithm for the for this problem. Okay, let's start coding. Let's start coding. So how do we solve this problem? So what we do here, first we will check the corner case if, okay, if rooms equals to none, or the rooms, the row of the rooms equals to 0, that means it's empty. And then this is the 2D gray. Okay, so the rooms, the column of the rooms, oh, sorry about that. The column of the room equals to 0. If in this corner case, what we just do, we just simply return. Okay, and then because we use the DQ, we use the Q, we use a Q data structure, DQ data structure to solve this problem. So it's gonna be like this. Okay, and then we initialize the how many the number of rows in this 2D grid. Okay, this column. So the column will be here, and then we iterate. Okay, so for this one, this is a corner case. We check if the room equals to none, or the row number, the row is empty, or the column is 0. So in this case, we just simply return, and then we will use a data structure DQ. The data type for the DQ is gonna be array here. Okay, in the array. Okay, the name we call it Q. And then we will get the row of the room's length, and then the column of the room's length. Okay. And then what we do, we iterate every single rooms in this cells. So we check if this one is equals to 0. If equals to 0, that means that's a gate. Okay. So we will offer the gate to our queue. Okay, this is basically this part we do. So we just offer all the gates in our queue. Okay, so and then what we do then, we clarify our for direction is a uh, uh, delta matrix. Okay, delta matrix is gonna be like this. So we have four direction, right? So what we do? 1, 2, 3, 4. So we put the four direction to here. So this one is a down direction. This up direction. This one is the right direction and the left direction. Okay. And then we have a initialize the step by 1 because we started from IG, right? So the IG, the first step is going to be 1, the length. Okay, and then what we do, we just check. We have a while loop. We just check if Q the size greater than 0. So that means it's not empty. If it's not empty, that means we are trying to pull everything one. So first, what we do, we get the size of Q dot size. So we get the size. What does that mean? Means that we are trying to get the size of every single level, for the BFS. Okay, and then we will pull every single cell from the current level. So that's why we got the size of Q. Because the size of Q actually is continuously updating. So we have to get it first, and then we iterating every single cells from the Q, every single element. Okay, so what we do, we iterating every single one. We are traversal every single element from the Q. I smaller than size, and then I plus. We have 4 direction. So and then after we pull this current cell out, based on the current cell, we will check the 4 directions. So here is d equals to 0, d smaller than 4. So what we do, we will do into new x. It's gonna be cur 0. Oh, cur 0 and plus delta. And then what we do, we will check new x. So this one actually we get the new actually the a cell what we trying to check, right? So we are trying to check if it's out of a boundary, or if it's visited, or if it's a block, So and then we decide how do we update it. So and then this one is out of boundary. So this one we are checking if our new cell is out of boundary. If out of boundary, we just continue. So this one actually we are checking here. We are checking if the cell we are going to check if is visited or not. So if not equals to the infinity, that means we already updated. That means we already visited. Okay, so it's already visited. If already visited, we just continue to check other directions. Okay, otherwise, if it's not out of boundary, is never visited. So that's if that's the first time to visit it. So what we do, we just pull it. We just actually add it to our queue, and then update our step. Okay. So what we do here, we just do this. New y equals to step. Okay, and then we queue the edit to our new inter array. So we, if never visited, it's not out of boundary. So we will update the step. Okay, for this current for this new cell, and then we will offer it. I mean, we will add it to the queue. Okay, this is basically what we do, and then we step plus plus. This was basically what we do. Okay, let's run the code. Let's run the code. So this one equals to this one, right? Step then this one. Okay, let's run the kill code. Common plus this one. Common plus this. Which one is common? Let's try this. Let's try this. Okay, sorry about that. I don't know why it's not working. Maybe I actually not even send in. Okay, so this is a problem for this question. I think this one is will work because I tried it before in some another kind of website. Okay, so I will log in maybe next time. After logging out, you just run the test and submit. Okay, so yeah, remember the time complexity for this problem is gonna be OMN because we iterating every single kind of the cell for just once, and then the space complexity will be OMN. This is basically the problem. Okay, thank you for watching. I will see you next time.